They'll tell you generation ships are humanity's ticket to the stars. They won't tell you about the mutinies, the genetic collapse, the children born into a metal cage who'll spend their entire lives maintaining a ship for a destination they'll never see. This isn't exploration, it's a multi-generational suicide pact. If you want to explore more mind-bending space science, please hit that subscribe button. You'll never miss another journey into the cosmos. Now let's get started. Generation ships represent humanity's most audacious dream, traveling to other star systems, not in our lifetimes, but over generations. These massive spacecraft would need to sustain entire civilizations for hundreds or even thousands of years as they crawl across the interstellar void toward distant exoplanets. Science fiction has painted these journeys as romantic adventures, but the reality is brutally different. The problems we face aren't just technical challenges we can engineer our way around. They're fundamental questions about biology, psychology, and what it means to be human. Here is something that sounds simple: keeping people alive. On Earth, you breathe air, drink water, and eat food. The planet's ecosystem recycles everything through natural processes that have been refined over billions of years. A generation ship needs to replicate this inside a sealed container perfectly, with zero margin for error, for centuries. One catastrophic failure means everyone dies. Scientists call these closed ecological life support systems, or CLSS for short. The concept sounds straightforward until you examine what it actually requires. Every breath you exhale contains carbon dioxide. Plants can absorb that carbon dioxide and produce oxygen through photosynthesis, but you need enough plants to match the oxygen consumption of your entire population. You also need to grow food, which requires even more plants. These plants need light, water, nutrients, and carefully controlled temperatures. They produce waste, which needs to be broken down by microorganisms and recycled back into nutrients. The water you drink today might have been someone's urine last week, and that same water might be inside a tomato next month. Here's where it gets disturbing. We've actually tried to build these closed ecosystems on Earth, and they've failed spectacularly. The most famous attempt was Biosphere 2, a massive facility in Arizona that sealed 8 people inside a 3.2-acre structure containing 5 different biomes: a rainforest, an ocean with a coral reef, a mangrove wetland, a savanna grassland, and a desert. The mission, which began in 1991, was supposed to last 2 years. It barely made it. Within months, oxygen levels started dropping. The researchers couldn't figure out why at first. Turns out the soil they'd brought in was packed with microbes that consumed oxygen faster than the plants could produce it. Oxygen levels fell from 21% to 14%, the equivalent of living at an altitude of 4,000 meters. The crew started suffering from hypoxia. They became sluggish, unable to think clearly. They couldn't even perform simple math. Eventually, mission control had to pump oxygen in from outside, completely defeating the purpose of a closed system. But the oxygen crisis wasn't even the worst part. Carbon dioxide levels spiked dangerously high in the mornings. The pH levels of the ocean went haywire, threatening the coral reef. 19 out of 25 vertebrate species went extinct inside the dome. Ant and cockroach populations exploded out of control. The crew started losing weight because they couldn't grow enough food. They split into factions and stopped speaking to each other. Some of them still don't talk to this day, decades later. And remember, this was happening on Earth, where if something went catastrophically wrong, they could just open a door and leave. Now picture that same scenario on a generation ship. There's no door to open, no rescue team, no backup oxygen tanks being delivered from outside. If your closed ecosystem collapses in interstellar space, everyone on board suffocates. There's no plan B. The European Space Agency recognized this problem and launched Project Melissa, the micro-ecological life support system alternative. They're trying to create a closed-loop system using microorganisms to break down waste and regenerate resources, It's essentially an artificial ecosystem in miniature. They've been working on it since 1989 and they still haven't perfected it. Think about that. We've spent nearly 40 years trying to build a system that nature does automatically, and we're still not there yet. On a generation ship, you can't afford decades of trial and error. The system needs to work perfectly from day one and keep working for centuries. Every component needs redundancy, every process needs backup systems. But here's the nightmare scenario scientists rarely talk about. What happens when something in your ecosystem evolves? Evolution doesn't stop just because you're in space. Bacteria, viruses, fungi, insects, even the plants you're growing for food are all evolving in response to their environment. In a closed system, that environment is radically different from Earth. There's cosmic radiation sleeting through the hull, altering DNA. There's limited genetic diversity, which accelerates genetic drift. There's intense selection pressure favoring organisms that can exploit any available niche. Over decades and centuries, the organisms on your ship will become something different from what you started with. Maybe a fungus evolves that's more aggressive, that can break down your composite materials. Maybe bacteria in your water recycling system develop resistance to your purification methods. Maybe a pest insect evolves faster reproductive cycles and starts devastating your crops faster than you can control them. You're basically creating a miniature petri dish of evolution, and you're living inside it. And speaking of things trying to kill you, we haven't even talked about what exists outside the ship yet. Space isn't empty, it's filled with radiation that makes Chernobyl look like a walk in the park. If you want to understand just how hostile the void really is, check out my video on the card above. It'll give you a whole new appreciation for the thin layer of atmosphere protecting us right now. The link is in the description. On Earth, we're shielded by a magnetic field and an atmosphere that blocks most cosmic radiation. A generation ship has neither. Cosmic rays, which are high-energy particles traveling at nearly the speed of light, slam into your spacecraft constantly. When they hit the hull, they don't just bounce off. They create cascades of secondary particles that penetrate deep into the ship. These particles rip through DNA, causing mutations, cancer, and cell death. Scientists working on relativistic spacecraft concepts like those proposed by Breakthrough Starshot have calculated what happens when a ship moving at even a fraction of light speed encounters the interstellar medium. In the ship's reference frame, every hydrogen atom in space becomes a deadly projectile. A ship traveling at just 10% of light speed would experience the equivalent of being constantly bombarded by a particle accelerator. The radiation produced would be intense enough to fry electronics and sterilize any biological material that wasn't adequately shielded. Generation ships wouldn't travel that fast. They'd crawl along at maybe 1 to 5% of light speed, but cosmic radiation is still a massive problem. Galactic cosmic rays originate from supernovae, exploding stars thousands of light years away. Solar energetic particles come from stellar flares. Both types of radiation are ionizing, meaning they strip electrons from atoms in your body, creating reactive molecules that damage your cells. To protect against this, you need shielding. Lots of it. We're talking meters of material surrounding the entire habitable volume of the ship. Water is actually one of the best shields because hydrogen atoms are effective at absorbing radiation. Some designs propose surrounding the crew areas with massive water tanks that serve double duty as radiation shielding and resource storage. Other concepts use regolith, basically dirt and rocks harvested from asteroids. The Project Hyperion design, a recent competition run by the Initiative for Interstellar Studies, proposed using a rotating Stanford torus design with extensive shielding integrated into the hull structure. But here's the catch: shielding is mass, and mass is your enemy in space travel. Every kilogram of shielding is a kilogram that isn't food, water, spare parts, or propellant. The rocket equation, formulated by Konstantin Tsiolkovsky in the early 20th century, tells us that the mass of your ship dramatically affects how much fuel you need to accelerate it. Adding more shielding means you need more fuel, which adds more mass, which means you need even more fuel. It's a vicious cycle that makes generation ships incredibly difficult to design. Even if you solve the engineering challenges, even if you build perfect radiation shielding and create a flawless closed ecosystem, you're still facing a problem that might be even more insurmountable. The human mind was never designed for this. Think about your worst day stuck inside during a lockdown. Maybe you felt claustrophobic, restless, desperate to go outside and see something, anything beyond the same four walls. Now multiply that feeling by an entire lifetime. You will never feel wind on your face, you'll never see a horizon, you'll never stand under an open sky. Every single day you wake up in the same enclosed habitat, seeing the same people, walking the same corridors. This is your whole universe. There's nothing else. Psychologists have studied what happens to humans in isolated and confined environments, or ICE, as researchers call them. They've looked at Antarctic research stations, submarines, and space station missions. The longest anyone has continuously stayed in space is 437 days, achieved by Valery Polyakov aboard the Mir space station in the mid-90s. He experienced psychological strain, but he knew he was going home. He could look out the window and see Earth rotating below him. He had regular communication with mission control. A generation ship offers none of these comforts. Research teams have conducted analog missions trying to simulate the conditions of long-duration space travel. The Mars 500 study, conducted by Russia's Institute for Biomedical Problems, locked 6 people in a mock spacecraft for 520 days. The HIC's missions in Hawaii isolated crews for up to 12 months in a dome on the slopes of Mauna Loa volcano. More recently, the Lunar Palace 365 experiment in China kept volunteers sealed inside a bioregenerative life support system for a full year. The patterns that emerge from these studies are deeply troubling. Researchers have identified what they call the third quarter phenomenon. During the first phase of isolation, people are excited and highly motivated. They're adapting to their new environment, establishing routines, bonding with their crew. This honeymoon period typically lasts a few weeks to a few months. Then comes the second phase, where reality sets in. The novelty wears off. People start to feel the monotony, but they're still coping, still functional. The third quarter is where things fall apart. This is when psychological distress peaks. People become depressed, irritable, and hostile. Sleep patterns deteriorate, cognitive performance declines, social conflicts intensify. In the Mars 500 study, crew members reported significant increases in stress and tension during this period. One crew member became so withdrawn he barely communicated with the others. Interpersonal conflicts erupted over trivial things like food preferences or cleaning schedules. And here's the terrifying part. These studies lasted at most a year or two. A generation ship journey to even the nearest potentially habitable exoplanet would take decades at minimum, possibly centuries. Proxima Centauri b, the closest confirmed exoplanet in the habitable zone, is 4.24 light-years away. Even traveling at 5% of the speed of light, which is wildly optimistic given our current technology, the journey would take 85 years. To reach more distant Earth-like candidates, you're looking at voyages lasting 200, 300, even 500 years. Nobody alive at launch would reach the destination. Your children wouldn't make it. Depending on the distance, it might take 10 or 15 generations before anyone sees the target world. How do you maintain psychological health across that kind of time span? How do you preserve motivation and purpose when the goal is so abstract, so impossibly distant? The people born on the ship, what researchers call intermediate generations, face an existential nightmare. They didn't choose this mission, They were born into it. They'll die in it. Their entire existence is to serve as a link between the founders who left Earth and the descendants who will colonize a new world. They're means to an end, living bridges between two groups who actually get to experience planetary life. How do you cope with that? How do you find meaning when your whole life is defined by something you'll never experience? Science fiction author Brian Aldiss explored this in his novel Non-Stop, published in 1958. The story follows descendants on a generation ship who've forgotten they're on a ship. Over generations, knowledge has degraded. Society has collapsed into tribal groups fighting over resources. The ship has become a world unto itself, a deteriorating metal jungle where the original mission is nothing but myth. And here's the kicker. When the protagonist finally discovers the truth, he learns the ship isn't even in transit anymore. It's been in Earth orbit for years. The crew can't be removed because they've genetically and psychologically adapted to ship life and are no longer compatible with Earth. That scenario isn't as far-fetched as it sounds. Cultural drift is a real concern. Over generations, knowledge can be lost, distorted, or deliberately suppressed. Languages evolve, religions emerge, political factions form. The society that arrives at the destination world might be radically different from the one that departed Earth, possibly unrecognizably so. In the Lunar Palace experiment, researchers studied gut microbiota and its relationship to psychological health in long-term confinement. They discovered that the isolation environment altered the crew's gut bacteria composition, which in turn affected mood and cognitive function. They identified potential psychobiotics, beneficial bacteria that could improve psychological resilience. But these findings also reveal how profoundly the closed environment changes you at a biological level. You're not just psychologically adapting, you're physically becoming something different. Now let's talk about something even more disturbing: governance and social control. How do you maintain order on a generation ship? What legal system applies? Who enforces it? On Earth, if you don't like your government or your society, you can move. You have options. On a generation ship, there's nowhere to go. You're stuck with whatever power structure exists for your entire life. What happens when conflicts arise that can't be resolved? What if a significant portion of the population decides they don't want to continue the mission? What if someone commits a serious crime? You can't exactly build prisons on a ship with limited space. You can't exile someone. Capital punishment becomes deeply problematic when genetic diversity is already constrained. Every person represents a significant percentage of the total gene pool. Some theorists have proposed authoritarian governance models for generation ships, arguing that democratic systems are too unstable for such a mission-critical environment. You need absolute certainty that decisions supporting the mission's success will be implemented regardless of popular opinion. But imagine being born into a dictatorship you can never escape, where dissent might be treated as mutiny, where individual freedom is subordinated to collective survival. It's a dystopian nightmare. Other researchers argue for highly participatory democratic systems where everyone has a stake in decision-making, fostering a sense of ownership and purpose. But democracies can be slow, contentious, and prone to making emotionally driven decisions that might endanger the mission. What if the population votes to turn the ship around? What if they vote to alter the mission parameters or abandon the destination? There's also the question of reproduction. On a generation ship, population size needs to be carefully controlled. Too many people, and you strain your life support systems. Too few, and you risk genetic bottlenecks and lose the labor force needed to maintain the ship. This means reproductive rights become a collective concern rather than an individual choice. Some authority, needs to determine who can have children and when. The genetics problem is staggering. Studies of generation ship viability, including recent work by researchers at the University of Strasbourg, have tried to calculate the minimum viable population for a multi-generational voyage. The numbers vary depending on journey length and assumptions about genetic management, but most estimates suggest you need at least several hundred people, possibly more than 1,000, to maintain sufficient genetic diversity and avoid inbreeding depression. Inbreeding depression occurs when closely related individuals reproduce, resulting in offspring with reduced fitness. Harmful recessive genes become more likely to pair up, causing genetic disorders, reduced fertility, and increased infant mortality. We've seen this in isolated human populations on Earth, island communities, religious sects, and royal families that practiced intermarriage all suffered from increased rates of genetic disease. On a generation ship, even with a starting population of 500 carefully selected individuals with maximum genetic diversity, you're going to see genetic drift. Random mutations accumulate. Some genetic lineages will die out by chance. Over generations, the population becomes more genetically homogeneous, and that's assuming everything goes perfectly. But there's another factor. Cosmic radiation causes mutations. Recent research published in the Astrophysical Journal examined radiation effects on relativistic spacecraft and found that cosmic ray impacts cause significant genetic damage. Even with shielding, some radiation gets through. Over generations, this leads to an elevated mutation rate compared to Earth. Most mutations are neutral or harmful. Only a tiny fraction might be beneficial. Scientists at INSERM and the Strasbourg Observatory included these radiation effects in their population genetic simulations for generation ships. They found that radiation-induced mutations affected life expectancy, fertility, pregnancy success rates, and miscarriage rates. Natural selection would work to eliminate the most harmful mutations, but the process is slow and imperfect. Over centuries, the cumulative genetic damage could compromise the population's viability. You might think you could solve this with genetic engineering and frozen embryos, bring along a genetic database and artificially maintain diversity, but that introduces its own problems. Who controls the genetic engineering? What traits get selected for or against? You're essentially practicing eugenics, making decisions about what types of humans should exist, and frozen embryos require continuous power and cooling for centuries. One equipment failure, one power loss, and your genetic backup is destroyed. There's also the unsettling question of genetic adaptation to the ship environment. Over many generations, natural selection will favor traits that increase survival and reproduction in that specific environment. Maybe people with lower metabolisms fare better with limited food resources. Maybe individuals with certain psychological profiles cope better with confinement. Maybe shorter stature becomes advantageous because it requires fewer resources. You're creating selection pressures that don't exist on Earth. By the time the ship reaches its destination, the population might be so adapted to ship life that they struggle to survive on a planet. Their immune systems might be naive to planetary microorganisms. Their bone density and muscle mass might be insufficient for higher gravity. Their psychology might be incompatible with open spaces. Brian Aldiss's fiction might become reality. The research on analog missions consistently shows that crew cohesion is critical for mission success. When crews bond and work together effectively, they cope with stress better. When they fragment into factions, performance deteriorates and psychological health suffers. On a ship with hundreds or thousands of people living for generations, maintaining social cohesion becomes exponentially more difficult. You'll have generational divides. The elders who remember the mission's purpose versus younger generations who see it as abstract. You'll have ideological differences, political movements advocating different visions for the society, religious or philosophical factions interpreting the mission through different frameworks, competition for resources, status, and mates. All the conflicts that plague human societies on Earth compressed into a sealed container with no release valve. Let's shift from the human problems to the machine itself. Because even if you somehow solve the psychological and genetic challenges, you're still trying to build a machine that needs to function perfectly for hundreds of years. Think about that. When's the last time you owned anything that worked flawlessly for even a decade without maintenance? Your car needs constant upkeep. Your phone becomes obsolete in a few years. Even the most robust infrastructure on Earth, bridges, dams, power plants, requires continuous inspection, repair, and eventual replacement. Now imagine a spacecraft millions or billions of kilometers from the nearest repair facility, unable to get replacement parts, operating continuously for 2, 3, even 5 centuries. The engineering challenge is almost incomprehensible. Let's start with propulsion. How do you even move something as massive as a generation ship? These vessels wouldn't be small. To house hundreds or thousands of people, along with all the infrastructure for a closed ecosystem, you're looking at structures that dwarf anything we've ever launched into space. We're talking about ships massing tens of thousands of metric tons, possibly hundreds of thousands. The International Space Station, humanity's largest space structure, has a mass of about 420 metric tons. A generation ship would be hundreds of times larger, and you need to accelerate this enormous mass to a significant fraction of light speed, ideally somewhere between 1 and 10%, to make the journey time even remotely reasonable. Chemical rockets are completely inadequate. The fuel mass required would be astronomical, literally larger than planets. The Tsiolkovsky rocket equation makes this brutally clear. To achieve even a tiny fraction of light speed using chemical propulsion, you'd need exponentially more fuel than ship, and it's physically impossible. Nuclear propulsion offers better possibilities. Project Orion, conceptualized in the late 1950s by physicists including Freeman Dyson, proposed using nuclear bombs. You'd detonate atomic weapons behind the ship, and a massive pusher plate would absorb the blast, converting explosion energy into thrust. Sounds insane, and in many ways it is, but the physics actually works. The numbers are staggering. You'd need thousands of nuclear devices, each detonated in a carefully timed sequence over years or decades of acceleration. The pusher plate would need to withstand repeated nuclear blasts without degrading. The crew would need to be protected from the intense radiation of each explosion, but theoretically you could achieve several % of light speed. Project Daedalus, designed by the British Interplanetary Society in the 1970s, proposed nuclear fusion propulsion. Instead of bombs, you'd use controlled fusion reactions, fusing deuterium and helium-3 in a reaction chamber and directing the exhaust out the back for thrust. The specific impulse, a measure of propulsion efficiency, would be far higher than chemical rockets. But here's the problem. We still haven't achieved sustained, controlled fusion energy generation on Earth, despite decades of research. The ITER fusion reactor, an international collaboration that's been under construction since 2007, isn't expected to achieve full fusion power until the 2030s at the earliest, and that's just for stationary power generation. Adapting fusion technology to spacecraft propulsion adds layers of complexity. Then there's the Bussard ramjet concept proposed by physicist Robert Bussard in 1960. The idea is elegant. Instead of carrying fuel, you scoop up hydrogen from the interstellar medium using enormous electromagnetic fields. You funnel this hydrogen into a fusion reactor and use the energy for propulsion. It's a self-fueling starship. The problem is that the interstellar medium is incredibly sparse. There's about 1 hydrogen atom per cubic centimeter on average, though density varies. To collect enough hydrogen for continuous fusion, you'd need a scoop thousands of kilometers wide. The electromagnetic fields required would consume enormous power, and recent analysis suggests that the drag from the scooping process might actually slow you down more than the thrust propels you forward. The physics might not work. Antimatter propulsion represents the theoretical ideal. When matter and antimatter collide, they annihilate, converting 100% of their mass into energy according to Einstein's equation, E equals mc squared. No other propulsion method offers that kind of energy density. A few kilograms of antimatter could accelerate a massive ship to relativistic speeds. There's just one tiny problem. Antimatter doesn't naturally exist in usable quantities anywhere we can access it. You have to manufacture it using particle accelerators, and the process is spectacularly inefficient. CERN, the European Particle Physics Lab, produces about 10 million antiprotons per minute. Sounds like a lot, right? But if you collected all the antimatter CERN has ever produced and annihilated it, it would barely power a light bulb for a few minutes. To fuel an antimatter rocket, you'd need grams or kilograms of the stuff. At current production rates and energy costs, creating even a single gram would take thousands of years and consume more energy than entire nations use. You'd also need to store it perfectly, because if antimatter touches normal matter, even a single atom, it explodes. You need magnetic containment systems that function flawlessly for the entire journey. One failure means your fuel annihilates your ship, so propulsion is an enormous challenge, but let's say you solve it. Let's say you achieve a steady acceleration to 5% of light speed using some combination of nuclear pulse propulsion and fusion drives. Now you have to maintain that speed for decades or centuries. That means your engines, your fuel systems, your power generation, everything has to keep working. Power is its own nightmare. A generation ship needs constant electricity for life support, lighting, computers, communications, food production, everything. Solar panels won't work once you're far from the sun. In interstellar space, starlight is so dim that solar power becomes useless. You need onboard power generation. Nuclear fission reactors are proven technology. We've used them on submarines and aircraft carriers for decades, but they require fuel, and fissionable material degrades over time. Uranium-235 has a half-life of 700 million years, so decay isn't the issue, but the reactor components themselves wear out. Control rods become brittle, cooling systems degrade, radiation damages structural materials. On Earth, nuclear reactors undergo regular maintenance and are typically designed for operational lifetimes of 30 to 60 years. After that, they're decommissioned. A generation ship reactor needs to last 10 times longer, and you can't exactly shut it down for refurbishment. You'd need multiple reactors with redundancy, the ability to switch between them, and a massive stockpile of replacement parts. Fusion reactors, if we ever perfect them, would offer longer operational potential because they produce less radioactive waste and cause less material degradation. But again, this is technology we haven't even successfully implemented on Earth yet. Some designs propose radioisotope thermoelectric generators like those used on deep space probes like Voyager and New Horizons. These devices convert heat from radioactive decay directly into electricity. They have no moving parts and can function for decades. Voyager 1, launched in 1977, is still transmitting data nearly 50 years later using RTGs, but RTGs produce relatively little power. Voyager's generators produce about 420 watts currently, down from their original output of 470 watts. That's less than a typical desktop computer. A generation ship needs megawatts of continuous power. You'd need thousands of RTGs, and the radioactive fuel, typically plutonium-238, decays over time, reducing power output. Then there's the question of maintenance and repair. Every mechanical system eventually fails. Bearings wear out, seals degrade, electronics malfunction. On Earth, you replace broken components. On a generation ship, millions of kilometers from Earth, you need to manufacture replacement parts on board. This means you need a complete industrial infrastructure on the ship. Machine shops, 3D printing facilities, electronics manufacturing, materials processing. You need stockpiles of raw materials, metals, polymers, ceramics, rare earth elements. You need people trained in every conceivable repair skill, and you need to pass that knowledge down through generations without degradation. Think about how hard it is to preserve technical knowledge even on Earth, where we have universities, libraries, and the internet. Ancient technologies like Roman concrete or Damascus steel were lost for centuries because the knowledge wasn't properly transmitted. On a generation ship, if expertise in repairing a critical system is lost, the consequences could be fatal. You also face the problem of technological obsolescence. The ship is designed and built using the best technology available at launch. But technology continues advancing on Earth. 20 years into the mission, Earth might develop far superior systems. 50 years in, the ship's technology might be hopelessly outdated. 100 years in, it might be primitive, but you can't upgrade. You're committed to the technology you launched with. This is called the incessant obsolescence problem. It's one reason some theorists argue that generation ships might never launch. Why commit to a centuries-long journey using current technology when waiting a few decades might yield vastly better propulsion or life support systems? If you keep waiting for better technology, you never leave. There's also the weight calculation problem. If Ship A launches now at 5% of light speed, and Ship B launches 50 years later at 10% of light speed thanks to improved engines, Ship B arrives first. So the pioneers who embarked on Ship A sacrificed everything for nothing. This paradox has led some to argue that generation ships are strategically irrational until we reach some theoretical maximum propulsion efficiency. Now let's talk about navigation and communication. Space is unimaginably vast and mostly empty, but it's not completely empty. There are dust grains, microscopic particles, occasionally larger debris. At 5% of light speed, which is 15,000 kilometers per second, even a tiny particle carries tremendous kinetic energy. A grain of sand massing 1 milligram hitting your ship at 15,000 kilometers per second would impact with kinetic energy equivalent to about 500 kilograms of TNT. That's enough to punch through metal hull plating. A pebble-sized rock would be like a nuclear weapon. Your ship needs forward shielding capable of vaporizing or deflecting these particles before they hit critical systems. Some designs propose using powerful magnetic fields to ionize and deflect charged particles. Others suggest a sacrificial shield, a thick mass of ice or metal positioned ahead of the ship to absorb impacts. The Project Daedalus design included a beryllium erosion shield at the front, but these systems add mass, and remember, mass is your enemy. You also need to navigate. In interstellar space, you can't use GPS. You need to track your position relative to known stars using onboard telescopes and computers. Course corrections require precise thruster burns. Miss your target by even a fraction of a degree early in the journey, and you'll be millions of kilometers off course by the time you arrive. And communication becomes increasingly difficult. Radio signals travel at light speed, which sounds fast, until you're light years away from Earth. A message from a ship 4 light years out takes 4 years to reach Earth, and another 4 years for the reply to come back. 8 years for a conversation. As the journey progresses, Earth becomes more and more distant, culturally and temporally. The society the crew left behind continues evolving. Political systems change, languages drift. Eventually, the people on Earth might have trouble even understanding transmissions from the ship. They're receiving messages from ancestors describing problems and referencing contexts that are generations out of date. And here's a disturbing question. Will Earth even continue supporting the mission? The initial generation might be invested, but 50 years later, 100 years, 200, why would people on Earth care about a ship that left before their great-grandparents were born? Funding and support could evaporate. Communication could cease. The ship becomes utterly alone. Beyond the particles and radiation we've already discussed, Space contains threats so catastrophic that a single encounter could end the mission instantly. Your generation's ship isn't just crawling through empty darkness, it's navigating a cosmic shooting gallery filled with hazards that could obliterate centuries of human life in a fraction of a second. Rogue planets are one such nightmare. These are worlds that have been ejected from their star systems, wandering through interstellar space in total darkness. Recent estimates based on gravitational microlensing surveys suggest there might be billions of rogue planets in our galaxy alone, possibly outnumbering stars. They emit almost no light and no heat. They're essentially invisible until you're right on top of them. Now imagine your generation's ship traveling at 15,000 kilometers per second, suddenly encountering a rogue planet in its path. At those speeds, you have virtually no time to react. Your sensors might detect the gravitational anomaly seconds before impact. That's not enough time to alter course. The ship slams into the planet and everyone dies instantly. Centuries of journey, dozens of generations erased in a moment. You might think the odds of hitting a planet are infinitesimally small, and you'd be right. Space is vast and planets are comparatively tiny, but over journeys spanning decades or centuries across light years of distance, those odds accumulate. It's like playing Russian roulette thousands of times. Eventually, probability catches up with you. Then there are stellar remnants. Neutron stars and black holes are the collapsed cores of dead stars. Neutron stars pack more mass than our Sun into its sphere only about 20 kilometers across. Their gravity is so intense that it warps space-time. Their magnetic fields are the strongest in the universe, trillions of times stronger than Earth's. Some neutron stars, called pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. If your ship passes too close to a neutron star, several terrible things could happen. The gravitational field could alter your trajectory, flinging you off course. The tidal forces could literally stretch and compress the ship, tearing it apart. The radiation from a pulsar beam could fry every living thing aboard and destroy all electronics. And like rogue planets, neutron stars can be difficult to detect if they're not actively pulsing or accreting matter. Black holes are even worse. Stellar mass black holes formed from collapsed massive stars can have event horizons just a few kilometers wide. Small and dark, they're nearly impossible to see unless they're actively feeding on surrounding material. Cross the event horizon, and physics as we understand it breaks down. You're crushed into a singularity. There's no escape, no survival, just absolute destruction. But you don't even need to cross the event horizon to be destroyed. Get close enough, and tidal forces rip you apart in a process astrophysicists gruesomely call spaghettification. Your ship would be stretched like taffy, with the end closer to the black hole, experiencing far stronger gravity than the end farther away. The structural stresses would tear the vessel into fragments, then atoms, then subatomic particles. The interstellar medium itself varies in density. Most of space is extremely sparse, but there are regions called molecular clouds where gas and dust concentrate. Some of these clouds are enormous, hundreds of light years across. If your trajectory takes you through a dense molecular cloud, the increased particle impacts could overwhelm your shielding. It would be like flying through a sandblaster at relativistic speeds. The drag from increased particle density would also slow you down. Remember, you've spent years or decades accelerating to cruise speed using precious fuel. If a molecular cloud saps your momentum, you'd need to fire engines again to regain velocity, consuming more fuel that you might not have. Your journey time extends, food supplies run low, and the mission enters crisis. Supernovae represent perhaps the most terrifying threat. When massive stars exhaust their fuel, they explode with unimaginable violence, briefly outshining entire galaxies. A supernova releases more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The explosion expels stellar material at speeds up to 30,000 kilometers per second, creating an expanding shockwave of superhot plasma and radiation. If a star goes supernova anywhere near your ship's trajectory, the radiation pulse arrives at light speed with no warning. Gamma rays, X-rays, and high-energy particles flood through the ship. Even with shielding, the radiation dose would be lethal. Everyone dies from acute radiation syndrome within days or weeks. If the expanding debris field catches up to you, the physical impact would destroy the ship. You might think you could predict which stars are likely to go supernova and plan your route to avoid them, but stellar evolution isn't perfectly predictable. A star might look stable when you launch, but go supernova 50 years into your journey. And some of the most dangerous supernovae, type Ia events, occur in binary star systems when a white dwarf accumulates enough material from a companion star to trigger runaway fusion. These can happen with little warning in systems that seemed stable. Gamma-ray bursts are even more catastrophic. These are the most energetic events in the universe since the Big Bang itself. They occur when massive stars collapse into black holes or when neutron stars collide. For a few seconds, a gamma-ray burst can outshine every other object in the observable universe combined. The beam of radiation is focused like a cosmic death ray, and if you're in its path, there's no survival. A gamma-ray burst within a few thousand light-years, if pointed at your ship, would deliver a radiation dose that would sterilize the vessel. We're talking about energy levels that would vaporize the hull. Even a burst from farther away could deliver enough radiation to kill the crew and fry all electronics. And because the radiation travels at light speed, there's zero warning. The first indication that a gamma-ray burst occurred is when it kills you. The unsettling reality is that we don't fully understand the distribution and frequency of these hazards. Our maps of the interstellar medium are incomplete. We've only detected a fraction of neutron stars and black holes in our galactic neighborhood. We don't know where all the rogue planets are. We can't predict all supernovae. A generation ship would be voyaging into partially charted territory, accepting risks that can't be fully quantified. Now let's talk about arrival, because even if everything goes perfectly, even if the ship survives the journey intact with a healthy population, you face an enormous challenge. How do you slow down? This is called the tyranny of the rocket equation. Part 2. You needed massive amounts of fuel to accelerate to cruise speed. You need just as much fuel to decelerate when you reach your destination. That fuel has to be carried with you for the entire journey, which means it had to be accelerated too, which required even more fuel. The mass ratios become absurd. Project Daedalus, designed for a flyby mission to Barnard's star, had a mass ratio of over 100 to 1. That means for every kilogram of payload, you needed 100 kilograms of fuel, and that was for a one-way, no deceleration probe. For a generation ship that needs to stop at the destination, the fuel requirements are exponentially worse. Some theoretical solutions involve splitting the mission into stages. You might decelerate using magnetic braking against the destination star's stellar wind, essentially creating drag against charged particles streaming from the star. Or you could use a magnetic sail to slow down, though this requires the destination system to have a dense enough stellar wind to be effective. Another concept is the Oberth maneuver, where you use gravity assists from planets or the star itself to shed velocity. But this requires precise navigation and favorable planetary positions, and it only works if the system's architecture allows for it. Not every star system has planets in the right orbits. Some designs propose sending the deceleration fuel ahead separately, slower-moving supply ships that arrive in advance and position themselves at the destination. The generation ship then uses this pre-positioned fuel to brake, but this requires two separate missions and assumes the fuel ships survive their journey and successfully position themselves. Here's an even more horrifying scenario. What if you can't slow down? What if your deceleration systems fail or you don't have enough fuel? You become a flyby mission by default. The ship screams past the destination star system at thousands of kilometers per second. You get maybe a few hours to observe the target planet as you hurtle past, and then you're gone, heading into the void beyond with no hope of return. The crew would have to come to terms with the fact that they'll never land, never walk on a planet. The entire purpose of the mission, the reason their ancestors left Earth, the goal that's defined their existence for generations, is now impossible. They're condemned to live out their lives aboard the ship, potentially for many more generations, until systems fail or resources run out. And here's something that keeps mission planners awake at night. What if you arrive at the destination and the planet isn't habitable after all? When you launch, you're targeting a world that's been observed from Earth. Maybe it's in the habitable zone of its star. Maybe spectroscopic analysis of its atmosphere suggests water vapor and oxygen. Maybe every indication suggests it could support life, but those observations were made from light years away. You're seeing the planet as it was years or decades in the past, because that's how long the light took to reach Earth. By the time you arrive, the situation might have changed. The planet's climate could have shifted. A runaway greenhouse effect might have turned it into a hellish Venus-like world. An asteroid impact might have sterilized the surface. Volcanic activity might have poisoned the atmosphere. Or maybe the planet was never actually habitable, and our initial observations were misinterpreted. We've already experienced this disappointment in our own solar system. Early telescopic observations of Mars suggested it might have canals and seasonal vegetation. Scientists in the late 19th and early 20th centuries genuinely believed Mars might host civilization. When robotic probes finally reached Mars in the 1960s and 70s, we discovered a frozen desert with a thin, toxic atmosphere. No canals, no vegetation, no Martians. Venus looked promising too, about Earth's size with a thick atmosphere. Some scientists speculated about tropical swamps beneath the clouds. Then the Soviet Venera probes landed in the 1970s and discovered an 800-degree furnace with crushing atmospheric pressure and sulfuric acid rain. The probes survived less than an hour on the surface. Now imagine discovering something similar after a century-long voyage. You've given up everything. Generations have lived and died for this moment, and when you finally arrive, the world is uninhabitable. What do? Your body is designed for Earth. Every system, every organ, every cell evolved over billions of years to function in one gravity environment with a 24-hour day-night cycle exposed to Earth's magnetic field and atmospheric pressure. A generation ship operates under radically different conditions, and those differences reshape human biology in ways we're only beginning to understand. Let's start with gravity, or the lack thereof. In microgravity, your bones don't need to support your weight. The constant stress that maintains bone density disappears. Your body responds by reabsorbing calcium from your skeleton at an alarming rate. Astronauts on the International Space Station lose 1 to 2% of their bone mass per month. In just 6 months, they can lose as much bone density as a postmenopausal woman loses in a year. For a multi-generational voyage, this is catastrophic. Even with rigorous exercise regimens, astronauts experience significant bone loss. Now imagine that continuing not for months, but for decades, for entire lifetimes. The first generation might maintain some bone density through constant exercise, but what about people born in low gravity? Their skeletons never develop the density that Earth-born humans have. Over generations, you'd see progressive skeletal weakening. That's why most generation ship designs incorporate artificial gravity through rotation. Picture a massive cylinder or torus, spinning around its axis. The rotation creates centrifugal force that mimics gravity. Stand on the inner surface and you feel pushed outward, simulating weight. This concept dates back to Konstantin Tsiolkovsky in the early 20th century and was refined by scientists like Gerard O'Neill in the 1970s. The O'Neill cylinder design proposes two counter-rotating cylinders, each 8 kilometers in diameter and 32 kilometers long. The rotation rate would be slow enough to avoid disorienting Coriolis effects, but fast enough to generate Earth-like gravity on the inner surface. You'd live on the inside of the cylinder, with the ground curving up around you in both directions. The Stanford Torus, designed during a NASA study in 1975, is a rotating wheel 1,800 meters in diameter. The Bernal sphere is a rotating hollow sphere 16 kilometers in diameter. Project Hyperion's recent competition explored similar designs. All of them use rotation to create artificial gravity, but rotating habitats introduce their own problems. The Coriolis effect, caused by the rotation, means that moving objects appear to curve. Throw a ball and it follows a curved path from your perspective. This is disorienting and causes motion sickness, especially if the rotation rate is too high. To minimize Coriolis effects, you need either slow rotation or a very large radius. Slow rotation means weak artificial gravity. Large radius means enormous structural mass. There's also a gravity gradient. If you're standing on the inner surface, your feet experience stronger simulated gravity than your head. In a small, rotating habitat, this difference can be significant and uncomfortable. Again, this argues for very large structures, which are harder to build and accelerate. Even with artificial gravity, you're not experiencing true gravity. The force is centrifugal, pushing you outward, not gravitational, pulling you downward. Your inner ear, which controls balance, can detect the difference. Some people adapt quickly, others never fully adjust. Chronic nausea and vertigo could plague certain individuals for their entire lives. And here's a troubling question. What about children conceived and born in artificial gravity? Their vestibular systems develop in this environment. Their brains wire themselves to this reality. If they ever experience true planetary gravity, they might be unable to function. They could be permanently adapted to ship life, physically incapable of transitioning to a planet. Muscle atrophy is another concern. In reduced gravity, your muscles don't work as hard. They weaken and waste away. Astronauts exercise for 2 to 3 hours every day using specialized equipment, and they still lose muscle mass. On a generation ship, maintaining this exercise regime for hundreds of people across entire lifetimes is a massive logistical challenge. You need equipment, space, time, and motivation. What happens to people who can't or won't exercise? The elderly, the infirm, the rebellious teenagers who refuse to comply? They waste away, becoming skeletal and weak. In a crisis requiring physical exertion, they'd be useless, potentially endangering the entire population. Cardiovascular systems change too. Without gravity pulling blood toward your legs, fluid shifts toward your head. Astronauts experience puffy faces and congested sinuses. The heart doesn't need to work as hard to pump blood upward, so it weakens. Blood volume decreases because your body thinks you have too much fluid. When astronauts return to Earth, they experience severe orthostatic intolerance, getting dizzy and fainting when they stand up because their cardiovascular systems can't cope with normal gravity. For generation ship populations, if the artificial gravity isn't perfect, you're looking at permanent cardiovascular changes accumulating over generations. Hearts that are smaller and weaker, blood vessels that don't maintain proper tone. People who would struggle or die if exposed to full Earth gravity. Then there's radiation, which we've discussed in terms of shielding, but let's talk about biological effects. Cosmic rays and solar particles ionize atoms in your cells. They damage DNA directly by breaking the molecular strands and indirectly by creating free radicals that attack cellular machinery. Your cells have repair mechanisms, but they're not perfect. Damage accumulates. Cancer is the most obvious consequence. Radiation-induced mutations can turn normal cells malignant. Studies of atomic bomb survivors and Chernobyl liquidators show clear dose-response relationships. More radiation equals more cancer. Astronauts on the ISS, protected by Earth's magnetic field and only exposed for months, show increased cancer risk. Generation ship crews exposed for lifetimes would face far higher rates. But cancer isn't the only problem. Radiation damages the cardiovascular system, increasing risk of heart disease and stroke. It causes cataracts, clouding the lens of the eye until vision is impaired. It affects the central nervous system, potentially causing cognitive decline, memory problems, and personality changes. Long-term, low-dose radiation exposure is associated with premature aging. Recent research from the University of Strasbourg modeled radiation effects on multi-generational populations. They found that even with moderate shielding, radiation-induced mutations affected fertility, pregnancy success, infant mortality, and lifespan. Natural selection would favor individuals with better DNA repair mechanisms, but the process is slow. In the meantime, you'd see increased rates of genetic disorders, stillbirths, and congenital abnormalities. Think about what this means for families. Higher miscarriage rates mean more grief, more psychological trauma. Children born with radiation-induced defects require medical care that strains limited resources. The cumulative psychological toll on a population watching their children suffer and die at higher rates than normal is devastating. And radiation doesn't just affect individuals, it affects the germline. Damage to sperm and egg cells gets passed to offspring. Mutations accumulate across generations. You could see hereditary cancers, genetic syndromes, and progressive degradation of the gene pool. This is eugenic pressure in reverse, an environment that systematically damages human genetics. Now let's talk about disease, because infectious diseases behave differently in closed populations. On Earth, epidemics eventually burn out. Susceptible people get infected, recover, or die, and the disease runs out of hosts. New people immigrate from unaffected areas. The population recovers. On a generation ship, the population is fixed. Everyone is exposed. If a disease is sufficiently contagious, it could sweep through the entire population in weeks. And there's nowhere to run, no outside help, no unaffected population to draw from. You might think you could prevent this by screening the initial crew for pathogens, creating a disease-free environment, but that's nearly impossible. Humans carry trillions of microorganisms in our bodies: bacteria, viruses, fungi, archaea. Most are harmless or beneficial, part of our normal microbiome. But under the right conditions, normally, harmless organisms can become pathogenic. Opportunistic infections occur when your immune system is weakened or your normal microbial balance is disrupted. Organisms that normally live on your skin or in your gut can invade tissues and cause disease. The stress of living on a generation ship, combined with radiation exposure and potentially nutritional deficiencies, could weaken immune systems across the population, triggering opportunistic infection outbreaks. There's also the problem of antibiotic resistance. Bacteria evolve rapidly, especially under selective pressure. If you use antibiotics frequently to treat infections, you create strong selection for resistant strains. On Earth, this is already a crisis. Antibiotic-resistant bacteria kill hundreds of thousands of people annually. On a generation ship, the problem is worse. You can't develop new antibiotics without sophisticated pharmaceutical research capabilities. You're stuck with the antibiotics you brought or can synthesize from limited resources. Bacteria will inevitably evolve resistance. Within a few generations, you could lose the ability to treat bacterial infections, sending medicine back to the pre-antibiotic era, where simple infections were death sentences. Viral diseases present different challenges. Viruses mutate even faster than bacteria. In closed populations, they can evolve to become more virulent or more transmissible. The confined environment with constant close contact creates ideal conditions for respiratory virus transmission. Imagine an influenza outbreak on a generation ship. On Earth, flu kills hundreds of thousands annually despite modern medicine. On a ship with limited medical facilities, a severe flu pandemic could kill significant portions of the population. And if the working-age population is decimated, who maintains the ship? Who grows the food? Critical systems could fail not from technical problems, but from lack of personnel. There's also the possibility of completely novel diseases. Microorganisms evolve in the ship's unique environment, potentially giving rise to new pathogens. The closed ecosystem, with its recycled water and air, its hydroponically grown crops, its confined animal populations, if any are brought along, creates novel ecological niches. Evolution fills niches. Something will adapt to exploit them. Fungal infections are particularly concerning. Fungi thrive in enclosed, humid environments. They're difficult to eliminate and can damage both biological and technical systems. On the ISS, fungi have been found growing on equipment, degrading plastics and electronics. Some species can cause serious human infections, especially in immunocompromised individuals. In a generation ship's recycling systems, fungi could contaminate water supplies or food production facilities. Airborne fungal spores could trigger allergies and respiratory problems. Pathogenic fungi, like Aspergillus or Candida, could cause invasive infections that are difficult to treat. And like bacteria, fungi can evolve resistance to antifungal medications. Mental illness is another disease category that concerns scientists. Depression, anxiety, psychosis. These conditions have genetic components but are heavily influenced by environment. The stressful, confined, monotonous environment of a generation ship is a perfect recipe for triggering mental health crises. We've already seen this in isolation studies. Antarctica winter over crews show increased rates of depression and anxiety. Submarine crews experience psychological strain. The longer the isolation, the worse the effects. Now extend that to lifetimes, to entire populations who never experience anything else. Without adequate mental health care, untreated psychiatric conditions could cascade into suicide, violence, and social breakdown. And mental health treatment requires trained professionals, medications, and therapeutic infrastructure. Maintaining these resources across generations is challenging. What happens when the ship's only psychiatrist dies and nobody trained to replace them? There's also the question of neurodegenerative diseases, Alzheimer's, Parkinson's, Huntington's disease. These conditions have genetic components. In a small, closed population with limited genetic diversity, deleterious genes can become concentrated through genetic drift and inbreeding. You could see higher rates of hereditary neurodegenerative conditions. And remember, this population is experiencing elevated radiation exposure and possibly nutritional limitations, both of which could increase neurodegenerative disease risk. An aging population with high rates of dementia would strain caregiving resources and reduce the effective workforce. Here's a question that cuts to the heart of the generation ship concept. Do the people born on the ship owe anything to the mission? They didn't choose to leave Earth. They didn't volunteer for this voyage. They were born into a situation created by their ancestors, condemned to live their entire lives in service of a goal they'll never see achieved. What moral authority compels them to continue? This is what philosophers call the consent problem. The original crew consented to the mission. They understood the sacrifice and accepted it. But their children, their grandchildren, 10 generations down the line, these people are conscripts, not volunteers. They're born into what amounts to a totalitarian system where their fundamental life choices, where they live, what they can do, even whether they can have children, are dictated by a mission plan created before they were born. Imagine you're born on such a ship. You grow up hearing stories about Earth, a mythical paradise your ancestors left behind. You're told about the destination world, a place you'll never see because it's still decades or centuries away. Your purpose, you're told, is to maintain the ship and raise the next generation who will also maintain the ship. You're a link in a chain, a means to an end. How do you find meaning in that? How do you cope with the knowledge that your entire existence is instrumental, that you matter only insofar as you serve the mission? This is an existential nightmare that no psychological preparation can fully address. Some theorists argue that the ship would need to develop cultural and religious frameworks that make the journey itself sacred. The mission becomes not just a voyage but a pilgrimage, a sacred duty passed from generation to generation. You might develop mythology around the founders, treating them as prophets or saints. The destination becomes a promised land, a heaven you're journeying toward, even if you personally won't arrive. This kind of cultural engineering might work for a while. Religions have sustained communities through hardship for millennia. The promise of future reward, even if you don't personally receive it, can motivate sacrifice. But it's also fragile. Religious movements splinter, evolve, and sometimes collapse. What happens when someone questions the doctrine? What happens when a charismatic leader reinterprets the mission or declares it void? History is full of isolated communities that maintain their identity for generations. The Polynesians navigated thousands of kilometers across the Pacific, maintaining their culture across vast distances. Religious sects like the Hutterites and Amish have preserved distinct ways of life for centuries. But these groups had something the generation ship doesn't: connection to a planet, to ecosystems, to the reality of Earth, even if they were isolated from mainstream civilization. On a generation ship, you're disconnected from everything humanity evolved within. There's no nature except what you've artificially created. There's no wilderness, no weather, no seasons except what's programmed. The sky is a metal ceiling. The horizon curves the wrong way. Every aspect of your environment is artificial and controlled. That kind of disconnection from natural reality could have psychological effects we can't fully predict. The sociologist Marshall Salins argued that hunter-gatherer societies were actually the original affluent societies because their needs were simple and easily met by their environment. Agricultural and industrial societies created artificial needs and dependencies. A generation ship takes this to the extreme. Every single thing you need to survive, air, water, food, warmth, is dependent on functioning technology. There's no safety net, no natural abundance to fall back on. This creates profound anxiety. On Earth, if civilization collapses, survivors can hunt, gather, farm. Nature provides. On a generation ship, if the systems fail, everyone dies. There's no backup plan. This existential vulnerability might create a society characterized by extreme risk aversion, where any deviation from procedure is treated as potentially catastrophic. But risk aversion can itself be dangerous. It stifles innovation and adaptation. What if the mission plan contains a flaw? What if circumstances arise that require creative problem-solving? A culture so focused on following procedure might lack the flexibility to respond to the unexpected. Alternatively, you might see the opposite: a culture of fatalism and nihilism. If your life is predetermined, if you have no real agency, why follow the rules? Why maintain the ship? Why have children who will face the same meaningless existence? This could lead to passive resistance, refusal to reproduce, or active sabotage. The mutiny scenario is terrifying but entirely plausible. A significant portion of the population, perhaps a majority, decides the mission is invalid. They don't consent to continuing. They vote to turn the ship around or alter course to a closer destination, or simply stop wherever they are and create a space habitat rather than completing the journey. What do the mission loyalists do? Do they have the right to compel the dissenters? Is it moral to imprison or even execute people who refuse to participate in a mission they never agreed to? But if the dissenters sabotage or redirect the ship, they're invalidating the sacrifices of everyone who came before. Both sides can claim moral authority. Science fiction has explored this repeatedly. In Arthur C. Clarke's Rendezvous with Rama, we glimpse generation ship societies that have diverged wildly from their original plans. In Harry Harrison's Captive Universe, the ship's population has regressed into primitive societies with no memory of the mission. In Kim Stanley Robinson's Aurora, the crew arrives at their destination only to find the planet uninhabitable, triggering a crisis over whether to attempt settlement or return to Earth. The return option is particularly interesting. If the journey is possible in one direction, it's theoretically possible in the other. What if, a century into the voyage, the population votes to go back? They've learned enough to know the journey is harder than expected. Maybe they've received transmissions from Earth describing fantastic technological advances. Why continue suffering when they could go home? But going back requires fuel for deceleration and reacceleration. It requires the ship to still be functional for another century-long voyage. It requires that Earth still exists and is willing to receive them. And it means admitting failure, abandoning the mission that previous generations died for. This decision would tear the society apart. Older generations who remember Earth, or at least heard first-hand stories, might desperately want to return. Younger generations who've only known the ship might fear the alien environment of a planet. Political factions would form. Violence could erupt. And here's the kicker. What if you turn around, make the century-long journey back, and when you arrive at Earth, the civilization you left is gone? Maybe there was a war, or environmental collapse, or they simply moved on and aren't interested in you. You've spent 200 years accomplishing nothing, and now you're stranded in your origin system with nowhere to go. The problem of mission drift is equally concerning. Imagine a game of telephone played across 10 generations. The original message gets distorted with each retelling. Now apply that to a mission plan. The founders understood the reasons for every procedure, every protocol. But as generations pass, that understanding degrades. Procedures become rituals performed without comprehension of their purpose. Maybe a critical system requires maintenance every 50 years, but by the third generation, nobody remembers why, just that it's tradition. If a charismatic leader declares the ritual unnecessary, people might stop doing it. Then, 50 years later, the system fails catastrophically because the maintenance didn't happen. Or consider the reverse, cargo cult thinking. Early in the mission, something broke and was repaired in a specific way. Future generations might treat that specific repair method as sacred, the only correct approach, even though better methods exist. They're imitating the form without understanding the function. Anthropologists have documented cargo cults in the Pacific Islands, where indigenous people observed Americans building airfields during World War II and receiving cargo deliveries. After the Americans left, some communities built replica airfields with bamboo control towers, thinking the ritual would summon cargo. They imitated what they'd seen without understanding the underlying mechanisms. On a generation ship, you could see similar phenomena. People performing technical procedures they don't truly understand, treating them as magic rituals rather than engineering. When those procedures fail or become obsolete, they don't know how to adapt. Education becomes critically important, but also problematic. You need to preserve technical knowledge across generations: engineering, medicine, agriculture, computer science, physics, all the specialized knowledge required to keep the ship running. But you also need culture, history, art, philosophy, the things that make life meaningful beyond mere survival. How do you balance that curriculum? How much time do children spend learning practical skills versus humanities? And who decides what knowledge is important? Education always reflects the values of those who design it. Whoever controls the curriculum controls the future society. There's also the problem of knowledge loss through disinterest. Maybe the third generation includes a brilliant physicist, but none of her children are interested in physics. That knowledge lineage breaks. Maybe there are textbooks and databases, but without someone actively engaged in the field, pushing the boundaries, the knowledge becomes static and eventually ossified. On Earth, we have universities, research institutions, millions of people pursuing every conceivable field. Collective human knowledge is distributed and redundant. On a generation ship with hundreds or a few thousand people, you can't have that diversity. You might have one engineer who understands the propulsion system, one doctor, one agricultural specialist. If any of them dies without successfully training a replacement, that expertise is lost. Cross-training helps, but nobody can know everything. Specialists develop deep expertise over decades. You can't just download that into someone else. And if your propulsion expert dies unexpectedly, the remaining crew might be able to keep things running based on procedure manuals, but if something goes wrong beyond the documented procedures, they're helpless. This is what engineers call single-point failures, but applied to human knowledge. Critical capabilities with no redundancy. It's a recipe for eventual catastrophic failure. Then there's the question of purpose and identity. Human beings need to feel that their lives have meaning. We derive meaning from relationships, achievements, contributing to something larger than ourselves. On Earth, you have infinite possibilities for finding meaning. You can pursue any interest, travel, change careers, reinvent yourself. On a generation ship, your options are severely limited. You can't leave. You can't change your fundamental circumstances. Your contribution to something larger is predetermined. Maintain the ship, support the mission. What if that's not enough for you? What if you want to be an artist in a society that values only engineers? What if you want solitude in an environment that requires constant social cooperation? The risk of depression, suicide, and general psychological malaise is enormous. You could see an entire generation lose the will to continue. Suicide rates spike, birth rates plummet. The society enters a death spiral where each generation is smaller and less capable than the last, until eventually there aren't enough people to maintain critical systems. Some designs propose addressing this with extensive virtual reality systems. Give people simulated experiences of Earth, of wilderness, of freedom. Let them escape the ship's reality into digital worlds where they can be whoever they want. But this creates its own problems. If the virtual world is better than reality, why engage with reality? You could have people spending all their time in VR, neglecting their duties. Or VR could become a tool of social control, an opiate keeping the masses docile. And VR systems require computing power, maintenance, and electricity, all of which strain resources. Let's say everything somehow works. Against all odds, the ship survives the journey. The population remains viable. Systems continue functioning. The descendants maintain mission focus. After centuries of travel, the destination star system finally appears ahead, growing brighter with each passing year. Arrival is imminent. This should be a moment of triumph, the culmination of humanity's greatest endeavor. Instead, it might be the beginning of an even more terrifying chapter. Because now you have to actually land on an alien world and survive there, and the people attempting this feat may no longer be physically capable of planetary existence. They've spent their entire lives, possibly multiple generations, in the artificial environment of the ship. They're adapted to controlled temperature, recycled air, artificial gravity, and a completely managed ecosystem. An actual planet is a hostile, alien environment to them. Let's start with gravity. Even if the ship has rotational artificial gravity approximating 1 g, it's not quite the same as planetary gravity. the Coriolis effects, the gravity gradient, the centrifugal force versus true gravitational pull. All these create subtle differences. Bodies adapted to artificial gravity might struggle with real gravity, and that's assuming the destination planet has Earth-like gravity. If the planet is more massive, surface gravity could be significantly higher. Imagine spending your entire life in 1G and then trying to function in 1.3 or 1.5 Gs. Every movement requires more effort. Your heart has to work harder to pump blood against stronger gravity. Your bones and joints experience greater stress. Simple activities become exhausting. People who've lived in the ship's artificial gravity for generations might lack the bone density and muscle mass to function in higher gravity. They might suffer stress fractures, joint damage, and cardiovascular strain. The elderly and the very young would be especially vulnerable. Landing on a high-gravity world could be medically catastrophic for a significant portion of the population. Lower gravity presents different problems. If the planet is less massive than Earth, colonists might find themselves dangerously strong and mobile. Jumps that seem normal could send you flying. Falls happen faster and harder than your instincts expect. And lower gravity means the planet likely has a thinner atmosphere, less protection from radiation, and potentially insufficient atmospheric pressure to support human life without assistance. Then there's the atmosphere itself. Even if the planet is in the habitable zone and has liquid water, its atmospheric composition might be very different from Earth's. Our atmosphere is about 78% nitrogen, 21% oxygen, and trace gases. We need that specific oxygen concentration. Too little and we suffocate. Too much and we risk oxygen toxicity and increased fire danger. The partial pressure of oxygen is what matters, not just the percentage. It's determined by both the oxygen concentration and the total atmospheric pressure. A planet with 10% oxygen but twice Earth's atmospheric pressure would have the same oxygen partial pressure as Earth. But breathing in such an atmosphere would expose you to higher partial pressures of other gases, which could be toxic. Carbon dioxide is particularly dangerous. On Earth, atmospheric CO2 is about 0.04%. At concentrations above 1%, it causes drowsiness and headaches. Above 5%, it's toxic. Above 10%, it can cause unconsciousness and death within minutes. If the destination planet has even slightly elevated CO2 levels, colonists would need respirators or atmospheric processing. Then there are gases that don't exist in Earth's atmosphere in significant quantities. What if the planet's atmosphere contains methane, hydrogen sulfide, ammonia, or other compounds? Even in small concentrations, many gases are toxic. You can't breathe an atmosphere until you've thoroughly analyzed it and confirmed it won't kill you. This means the initial landing parties need protective equipment, spacesuits or at minimum respirators, pressure suits if atmospheric pressure is wrong, and extensive monitoring equipment. But here's the problem. People who've spent their entire lives in the ship's controlled environment have weak immune systems with no exposure to alien microorganisms. When Europeans reached the Americas, they brought diseases that decimated indigenous populations who had no immunity. Now imagine the reverse, colonists from a sterile spaceship environment encountering a planet teeming with alien microbial life. Even if the microorganisms didn't evolve to infect humans, some might be capable of doing so. Panspermia theories suggest that basic biochemistry might be universal, that DNA or similar molecules could be common throughout the galaxy. If the destination planet has life based on similar biochemistry, there's a real possibility of cross-species infection. Alien bacteria might find human bodies hospitable. Alien viruses might be able to hijack human cells, and the colonists would have no immunity whatsoever. No evolutionary history with these pathogens, no antibodies, no resistance. A microorganism that causes mild illness in the planet's native life could be catastrophically lethal to humans. This is the plot of The War of the Worlds in reverse, where the invaders are killed by microorganisms they have no defense against. Planetary quarantine protocols would be essential. Initial exploration teams would need to work in complete biological isolation, conducting extensive studies before direct environmental exposure. But maintaining quarantine is difficult. A single breach, one torn glove, one failed airlock seal could expose the entire population to alien pathogens. And here's a darker possibility. What if the planet already has intelligent life? Not necessarily technological civilization, but sentient beings with their own claims to the world. Does humanity have the right to colonize an inhabited planet? This is colonialism on a cosmic scale, potentially displacing or destroying native life to make room for humans. The ethical implications are staggering. If the native life is microbial or simple plants, maybe you can justify it. But what if there are complex ecosystems? What if there are animals with apparent consciousness? What if there's intelligent life that simply hasn't developed technology we recognize? Do you have the moral right to proceed? Some of the colonists, especially those born on the ship, who've lived their entire lives dreaming of setting foot on a world, might not care about ethical niceties. They've sacrificed everything for this moment. Their ancestors died for this. They're not turning back because of alien bacteria or indigenous slugs. This creates moral conflict within the population, potentially leading to violent schisms. Let's assume the planet is lifeless, or you decide to proceed anyway. Now you have to actually establish a colony, and this is where things get truly difficult, because everything you need to survive has to either be brought from the ship or manufactured from local resources, and both options are problematic. The ship carried everything needed for the journey: food production, water recycling, life support, power generation, but it wasn't designed to be disassembled and repurposed as a planetary colony. The systems are integrated, designed to function in space. Removing them potentially cripples the ship, and you might still need the ship for orbital infrastructure, or as a fallback if the planetary colony fails. So you need to establish ground-based infrastructure while maintaining the orbital ship. This requires dividing your already limited population. Some people stay on the ship maintaining systems, others descend to the surface to begin construction. You're spreading your limited human resources across two separate environments, each with its own challenges. On the surface, you need shelter, radiation protection if the planet lacks a strong magnetic field, temperature regulation if the climate is harsh, atmospheric processing if the air isn't breathable, power generation, probably solar if the star is suitable, or nuclear using reactors from the ship, water extraction and purification, agriculture to produce food. All of this requires equipment, materials, and energy. You're essentially trying to establish an industrial civilization from scratch with a tiny population and limited resources. On Earth, human civilization developed over thousands of years through the accumulated effort of millions of people. You're trying to replicate that with hundreds or a few thousand individuals. The comparison to historical colonization is instructive but not encouraging. When Europeans colonized the Americas, they had enormous advantages. They arrived on a planet perfectly suited to human life. They could breathe the air and drink the water. Native plants and animals were edible. They had continuous resupply from Europe. Even with all those advantages, early colonies had horrific mortality rates. Jamestown lost 80% of its population in the first year. Roanoke disappeared entirely. Now attempt colonization on an alien world where nothing is guaranteed compatible, where the soil might lack essential nutrients or contain toxic minerals, where native plants, if any exist, are almost certainly inedible and possibly poisonous, where water sources might be contaminated with alien microorganisms or dissolved compounds harmful to human biology, where you have no resupply, no reinforcements, and no escape if things go wrong. Food production is particularly challenging. If you brought seeds from Earth, will they grow in alien soil under an alien sun? The planet's star might emit a different spectrum of light than our sun. Plants evolved to photosynthesize under Sol's specific spectrum might be inefficient or unable to function under a different star. The soil chemistry might be completely wrong. Earth's soil is alive, teeming with bacteria, fungi, earthworms, and countless microorganisms that break down organic matter and make nutrients available to plants. Alien soil might be sterile, mineral dust, lacking the biological activity that makes Earth's soil fertile. You'd need to terraform the soil, introducing Earth microorganisms and organic matter, which takes time. The day-night cycle might be wrong. If the planet is tidally locked to its star, one side experiences permanent day and the other permanent night. The habitable zone would be the narrow twilight band between them, with constant wind as air circulates between the hot and cold hemispheres. Growing crops in that environment would be extremely difficult. Even if the planet has a day-night cycle, the length might be very different from Earth's 24 hours. Plants have circadian rhythms tuned to Earth's rotation. Dramatically different day lengths could disrupt their growth cycles. You might need to grow everything in controlled environment agriculture, essentially greenhouses with artificial lighting, which requires enormous energy inputs. Hydroponics and aeroponics, growing plants without soil, might work better than trying to use alien soil. But these systems require water, nutrients, energy, and maintenance. They're technologically intensive. If your equipment fails and you can't repair it, your food production collapses. And then there's the question of genetic diversity. Remember, your crop seeds were brought from Earth, a limited supply with limited genetic diversity. You can't just order more varieties. If a disease or pest affects your crops, you might not have resistant varieties to fall back on. A single agricultural disaster could cause famine. Animal husbandry faces similar problems. You might bring frozen embryos of livestock, chickens, pigs, cattle, trying to establish sustainable animal populations. But animals need food, which means growing feed crops. They need grazing land or housing. They produce waste that needs to be managed. And small populations face the same inbreeding problems humans do. More fundamentally, after generations in space eating vat-grown protein and hydroponically grown vegetables, do the colonists even know how to raise livestock? Do they have the cultural knowledge and practical skills? These aren't things you can just learn from textbooks. They require hands-on experience passed from generation to generation. The timeline for establishing a self-sustaining colony is decades at minimum, more likely generations. During that entire period, the colony is vulnerable. A single catastrophic failure, a crop disease, a reactor malfunction, a medical crisis could cause total collapse. And unlike the ship, which was engineered with redundancy and closed-loop systems, a planetary colony is exposed to countless variables you can't control. Weather is one such variable. The planet has a climate, but you don't fully understand it yet. You've observed from orbit, but local conditions can be radically different from global patterns. You might establish your colony in what seems like a temperate zone, only to discover it's subject to hurricanes, tornadoes, or seasonal floods. Your infrastructure gets destroyed, crops are wiped out, and people die. Geological activity is another threat. Earthquakes, volcanoes, tsunamis if you're near a coast. The planet is geologically active, which is good because it suggests a magnetic field and active carbon cycle, but it also means the ground can literally open up beneath you. Building in a geologically stable zone requires extensive surveying and understanding of the planet's tectonics, which takes years of study. And here's perhaps the most psychologically devastating possibility. What if, after all this, colonists simply can't adapt? What if children born on the planet have higher mortality rates? What if the adults, after lifetimes in the controlled ship environment, can't cope with the variability and unpredictability of a real planet? The horrors of deep space get even worse. Click the video on your screen to see the biological nightmares that make generation ships look easy. Discover why leaving our solar system might be humanity's most impossible dream. You need to watch this.